There is a road in Norway that doesn't touch the ground. It sits on water, miles of it, and it moves. Not because something went wrong, because that was always the plan. Norway has one of the most jagged, fractured coastlines on the planet. Hundreds of fjords cutting deep into the land, some of them too wide to bridge, too deep to tunnel, too cold to ignore. For decades, the only way across was a ferry. You would drive to the edge of the land, wait, board a boat, cross, and drive again. Millions of people, every year, just waiting. What if the road itself could float? Not a boat, not a bridge, not a tunnel, a highway, on the ocean, anchored to nothing but physics and nerve. What followed was one of the most quietly ambitious engineering projects in modern history, and almost nobody outside Norway knows it exists. Norway has 1,100 fjords. Some are narrow enough to bridge, some are shallow enough to tunnel beneath, but a handful of them are different. They are wide, they are deep. In some places, the water below drops to over 1,300 meters. You can't anchor a bridge to a seafloor that far down. The forces involved would tear the structure apart before the first winter ended. And tunneling? Engineers tried. In some fjords, they dug submarine tunnels that plunged 200 meters below sea level just to get a car from one side to the other. It works, but it's expensive, it's slow to build, and it has limits. Norway's western coastline stretches for thousands of kilometers. The country needed a continuous highway, Route E39, running from Kristiansand in the south all the way up to Trondheim in the north. A drive that should take about 21 hours, but because of the fjords, it takes 26, sometimes more. Those extra hours aren't just inconvenient. They represent billions of dollars in lost productivity, delayed freight, and wasted fuel every single year. So the Norwegian government made a decision. They would build the world's first floating bridge highway across open fjords. Not one bridge, several, stretching across water that no conventional structure could cross. The concept had existed in engineering theory for years, but theory and reality are two very different things, because there was a problem no one had fully solved yet. And it wasn't the water. It was what the water does. The ocean doesn't stay still. That's the problem every engineer on this project had to confront before drawing a single line. Fjord water moves. It swells. It contracts with temperature. Tidal forces push and pull the surface by half a meter or more throughout the day. And then there are the storms. Norway's western coast sits directly in the path of North Atlantic weather systems. Winter storms roll in fast. Winds hit 40, sometimes 50 meters per second. Waves build not from the open sea, but from the fjord itself, bouncing off cliff walls, colliding with each other, creating chaotic, unpredictable surface patterns. A floating bridge in that environment doesn't just need to hold weight, it needs to flex. That was the insight that changed everything. Norwegian engineers at the Public Roads Administration began modeling a structure that wouldn't fight the water. It would move with it, slightly, controlled, within precise tolerances that kept the road surface stable enough for vehicles traveling at highway speed. The design they settled on used large, hollow concrete pontoons, essentially sealed floating cylinders, anchored beneath a continuous curved bridge deck. The curve wasn't aesthetic, it was structural. A straight floating bridge and moving water would buckle. The arc distributed stress across the entire length. On paper, it worked, but one engineer reviewing the stress models noticed something the simulations hadn't fully accounted for: resonance. When waves hit a floating structure at the right frequency, they don't just push it, they amplify it, each wave adding energy to the last. The movement grows, slowly at first, then faster. It's the same physics that can collapse a suspension bridge, and no one was certain yet how to stop it. Resonance had already destroyed a bridge once before. In 1940, the Tacoma Narrows Bridge in Washington state began oscillating in moderate wind. Not a storm, just steady, rhythmic wind hitting the structure at the wrong frequency. Within hours, the entire span was twisting like a ribbon. Then it fell. Norwegian engineers knew that story well, and they knew a floating bridge presented an even more complex version of the same problem. Because unlike a suspension bridge, a floating structure is coupled directly to the water. Every wave is a potential input, every storm a potential trigger. The lead engineering teams ran thousands of simulations, They tested scale models and wave tanks at research facilities in Trondheim and Delft. They adjusted pontoon spacing. They modified the curvature of the deck. They added damping systems inside the bridge structure itself, mechanical components designed to absorb energy before it could build into something dangerous. Each test revealed something new, and not always something reassuring. One set of wave tank results showed that under a specific combination of wave height and wave period, conditions that occurred in Sognefjord roughly 4 to 6 times per year, the bridge deck would experience vertical movement of nearly 1 meter. 1 meter at highway speed. The project lead reviewed those numbers quietly. He didn't cancel the project, but he didn't dismiss the finding either. He ordered a redesign of the pontoon configuration. It delayed the timeline by 8 months. What no one said out loud was the question that sat in the room during every review meeting. They were solving for the conditions they could measure. But Sognefjord had a history of producing conditions that didn't show up in any model. Sognefjord is not an ordinary body of water. It is the longest fjord in Norway, over 200 kilometers from its mouth to its inner end. In places, it drops to 1,308 meters deep. That's deeper than the tallest building on Earth is tall. And beneath that depth, something unusual happens to the water itself. Sognefjord has distinct water layers. Cold, dense salt water sits at the bottom, largely undisturbed for decades at a time. Above it, lighter, fresher water from glacial runoff sits closer to the surface. These layers don't mix easily, but occasionally, large storm systems push enough surface water toward the inner fjord that the pressure differential forces a deep water exchange. Cold bottom water surges upward. The surface destabilizes. Water temperature shifts rapidly across the entire crossing zone. When engineers first reviewed historical oceanographic data for Sognefjord, one researcher flagged a documented event from 1990. A deep water exchange had occurred during a winter storm. Surface current speeds during that event reached nearly 4 knots, fast enough to exert significant lateral force on any structure sitting in the water. 4 knots doesn't sound like much, but applied across 4,600 meters of floating bridge deck, the cumulative lateral load becomes enormous. The pontoon anchoring system had been designed for 2 knots. The entire anchoring calculation had to be revisited. New mooring line configurations were drawn up, heavier, deeper, more redundant. The cost climbed again, but the engineers signed off. The models held. Construction was finally approved, and in 2023, work on the Sognefjord crossing began in earnest. Everything looked controlled, precise, accounted for, until the first winter on site. The first winter hit harder than the forecast suggested it would. A storm system stalled over the Norwegian Sea in January. Instead of moving through in 36 hours like most systems, it sat for 6 days. Wind, waves, sustained surface current that pushed against the partially constructed pontoon sections with a force the on-site crew had not yet experienced. One of the senior construction supervisors later described watching the pontoon segments move in the water that week, not violently, quietly, a slow, rhythmic shifting that shouldn't have been happening at their mooring tolerances. He ordered work suspended until the storm passed. When the engineering team reviewed the motion data recorded during those 6 days, they found something that gave them pause. The pontoons had moved within the acceptable limits, just barely, but the data also showed a pattern, a low-frequency oscillation building across 3 consecutive days before damping out. It was resonance, early stage, self-correcting in this instance. But the word "this instance" carried weight. The damping systems were recalibrated. Additional sensors were installed across every pontoon segment. A real-time monitoring protocol was established. If movement thresholds were crossed, traffic would be halted automatically before any driver felt anything unusual. The project continued, and that, quietly, is the point. This bridge isn't finished yet. The full E39 floating crossing at Sognefjord is projected for completion in the early 2030s. But the engineering framework is real. The challenges are documented. The solutions are being tested right now on water in real Norwegian winters. No country has done this before at this scale. Norway is doing it anyway, not because it's easy. Norway decided they weren't. If you want to follow more stories like this, real engineering, real stakes, real consequences, there's a subscribe button. It exists for exactly this kind of story.